Okay, here's a quick video on exponential growth and decay, and then I'll try to throw a few logs in there too to help you out. So the nice thing is it's pretty much easier to write an equation or a function, whichever notation you want to use here, for exponential growth, because you always have a starting amount, a multiplier, and then you have an exponent. So again, if you want to use y or f of x, that really doesn't matter. I'm going to use f of x just because we're kind of talking about functions in class, but it doesn't matter. So I need a starting amount. So let's say that it says something about a car being worth, say, $20,000 when you buy it, or maybe you buy it used, whatever. So that's your starting amount. And then your multiplier is what's happening to it every time period. And so this is an 8% depreciation, meaning it's losing 8% every year. So if it starts out at 100% of its value and it's losing 8%, then you're really only keeping 92% of the value. So that would go right there. That's your multiplier, because after 1 year, you would keep 92% of this value. 2 years, you'd multiply by that twice. 3 years and 4 years and so forth. So you take that 20,000 times 0.92, 0.92, 0.92 for, say, 3 years. And so my exponent is up here. And in this case, it's happening every year. So I'm just going to use x. And so then I can use this formula, and that's kind of a bad x. So let me fix that a little bit here. So I can use this formula. So say I want to know, what is the cost of this car going to be in 10 years? Well, if this function holds, then I could shove in and substitute in 10 where my exponent is. So on my calculator, I would take 0.92 to the 10th power. And again, order of operation, you would do this part first and then take it times the 20,000. And then you would have a value of what the car is at that point in time. And then the reverse could happen. I could say, okay, when is the car going to be worth, say, $10,000 if, again, this function holds. So that's the output. So here I was giving you the input, but now I'm giving you the output. When is it going to be worth 10,000? So you could set up your equation. And I'm just going to erase this up here so it kind of doesn't get in our way at all. All right, and so there's x. So this is where you can just guess and test, you know. So you could see what our answer is for 10 years and then go from there. So you could guess 10 years, 20 years, 30 years, 21, 22, until you get it to work. The other option is to use logs, and we'll talk about that in a little bit. All right, let's look at the second example here. So a house appreciates 5% every year. So it's actually getting worth more every year. And so say you buy a house for $150,000. Okay, and that's your starting amount. So again, your function, f of x equals, it's always your starting amount, your multiplier, and then your exponent. So this house is starting at $150,000. Now, this time it's appreciating, which means it's getting worth more money. So I have my 100% and it's going up. So my multiplier is actually 105% because I get to keep the old value, but then I get to keep adding that 5% all the time. So as a decimal, that would be my multiplier. And then again, my time is this is happening every year. So again, I could say, okay, well, what was this house worth if x is 0? Now again, x equals 0 is at the start of time, or at the start of the function. And so if I sub that in for my input, anything to the 0 power is 1, that's going to give me my output of $150,000, which is what I want. Because if no time has gone by, then that house should be at that value. Or again, you could say, okay, what is it going to be worth in 5 years? Again, you'd sub in 5 for your variable, and basically that would do that 105% over and over and over again, and you would get what the output is today. And I didn't bring my calculator home with me, so you guys can, you know, type that in and see what you get. All right, so real quick, logs. Let's talk about logs, because again, on this house problem, I could say, okay, assume this function works for a long period of time, and I could say something like, okay, well, when is this house going to be worth $200,000? So again, without logs, you're going to have to just guess and test. So you're going to have to sub in some value for x. Again, that's going to happen first, then multiply by your starting amount, see if it equals 200,000. And then guess again, and guess again, and guess again, and so forth. And it can be kind of time consuming. So this wonderful thing called logarithms was invented, and it is the greatest thing since sliced bread. So let's just make sure you understand those quick. So if I give you 2 to the third, that equals 8. And for, I don't know, as far as some real vocab here, this guy is called your base. This is your exponent. And for lack of a better term, we're going to call this guy the answer. All right. And so what do logs do? Well, logs are wonderful because they get this exponent down kind of on the level. And so what logs do is logs eat up the answer and they spit out the exponent, which is awesome. And then the base just kind of goes down here. So for example, for this problem over here, the log would eat up the 8, and it's going to spit out the 3, and then the base is, what, 2 there. So we would write it like that. All right, and to check that on your calculator, we have this wonderful thing called the change of base formula. So you're going to take the log of 8 divided by the log of 2, and if that doesn't equal 3, we're in trouble. But it should, because obviously 2 cubed gives us an answer of 8, so that's a good thing. All right, so let's look at how you are going to apply this. So I'm going to erase a little bit so we can kind of, let's see, go back to this example, and you guys can try this on your calculator. All right, here we go. So I raised up this scenario, and we talked about how you could guess and test. So instead, we're going to use logs, but logs have to be set up where you have base, exponent, and an answer, and right now we don't have that because we have this number here. So we are going to divide both sides by that guy to get rid of it. Those cancel, and let's see that, and that. Those all cancel. And so let's see, what do I get? If I divide by 5 and divide by 5, I would get, what, 4/3? And there's the rest. Okay, so I want to figure out what my exponent is here, but I don't want to sit there and guess and test over and over and over again. I can, all right? There's nothing saying that you cannot say, this is what, 1.333 repeating. So, you know, this has to be less than 1, right? Because to get that to happen, because to the first power, oh, sorry, I mislooked. That would have to be bigger than 1, because this would be 1.3, and so I need a little bit more. But, you know, guessing and testing could be a pain. So instead, if you know logs, it's a wonderful thing. All right, so let's use our log knowledge here. So this is what I would call the answer. And this is called the base by everybody. And this is called the exponent by everybody. All right, so what you would do is you would say, awesome, logs exist. So you're going to take log. And logs always eat up the answer. And they always spit out the exponent, which is wonderful because then your x is down on the level where you can do some math. And then your base always goes down here. All right, so what you're going to have to do on your calculator is take the log of 4/3 divided by the log of 1.05. And when you get that answer, that is your exponent. And you can get it without guessing and testing. You can actually just do log of the answer over log of the base, and it will spit it out for you, which is a lovely, lovely thing.